Okay, so there's one other topic in chapter 2 that we are going to cover. And before we go to the chapter 3, the last topic that we'll cover in chapter 2 is dot product. And you most likely had it in the mathematics course for physics. So if I have two vectors, then vector A, vector B, and the angle between them is going to be theta. So if I have it like that, I can say that the A dot B is A, B cosine theta. One thing that I want to mention that this is scale. So it's not a, it is not a vector. So you remember that if you have a dot product, the result is just a number. Because it's going to be 10, 5, something like that. But it's not going to be a vector like that. If I go ahead and say, assume I write the A, I write them in Cartesian form. So, okay, so AXI plus AYJ plus AZ in K, and then similarly the BXI plus BYJ plus K direction. So if I write it like that, I know that I dot I J dot J dot K is 1, and I J I K J K is 0. So if I put these 4 conditions together and write it A over B, so I can say A dot B say that is going to be the AX BX plus AY BY plus AZ BZ. So another way, so I have this BB and that as well. Any question? If I have that equation, look at that equation, from that equation, go ahead, I can find the theta on that. So basically, if you look at that equation, so A, B is A, B cosine theta, therefore the cosine theta is A dot B divided by AB. And from there, I can find the theta, so I can say theta will be sine inverse of AB divided by. So if I have So I have two vectors and I want to find the angle between them, I can find it like that also. So you can, so you have two vectors and you want to find the angle between them, you can, sorry, this as a dot, so it's A dot B. Any question?
Are we gonna do like an example of this?
We will do the example on this, but we probably never use it again.
Okay.
So next, if I have x and y, and then I have the vector A here, and then I have the vector say, u in x direction, or let's make it u and v, so it's not x and y, so u axis and v axis. Any two axes that are perpendicular to each other. And then I have a u along the u axis. That's a unit vector. And there's going to be unit vector here u along the v axis. If I go ahead and write A, what's the A dot u gives me? A dot u will give you. So it's going to be the magnitude of the A, the magnitude of the u, and the cosine theta, assuming this is theta, correct?
Yeah.
So what's the magnitude of the u?
1.
The unit vector, so it's going to be 1. So the magnitude of the u is 1. So it's going to be A cosine theta. So what's A cosine theta? A cosine theta is this A cosine theta?
Yes.
So A dot u gives you the projection on that axis. So it says A dot u. So if you have the vector and dot product with the unit vector on that axis, it gives you the projection on that axis. And from there, that's nothing to do with this one, but if you want to find, for example, this one, okay, this one as well. So it's, I call it perpendicular one. It's just A perpendicular one is the A minus A on U. In case they want to calculate. But this is A on, this is A. The V project and the U projection. And where I got that, let's just write it the other way so it's easier. A dot U plus A dot V. Agree?
Yeah.
So you can just call it, say A dot U, which is A minus dot U. A on the V axis. So this one you already know. If you multiply the length of the vector by the cosine, it gives you the projection.
So if we wanted to get AV before we got AU, would we be allowed to just use A sine theta, or does that not really work with dot product? Because dot product is automatically cosine.
This is eventually what we do, because as I said, we're not going to use the dot product. We're using the cosine and the sine. But if you want to go through the dot product, this is how you have to do it.
Okay.
That's why we are not doing the dot product.
Fair.
If I have, for example, two axes like this, let's call it U and V, and again, the same two axes, U and V, and I would have F here, the same F here. Now if I go ahead and plumb it. Parallel. So what's the difference between these two?
One on the left doesn't seem right, based off what we've done in the past, because it is using right angles to do the stuff when really we want to be doing parallel.
So this one is not right, or this one?
That one's correct. That other one, I
That
don't
other
know what's
one's
going
right.
on.
So what's the difference then?
The lines, those dashed lines aren't correct of the left one. I don't know why, but they're kind of disturbing.
So this one, if I call it FU and this call it FV, this one is the, let's just see what the book call it. So FU projection is the FV projection. So the one on the left, which is as the right angle, is the projection of the vector on this axis. So these are the projection on the axis. These are the components.
Okay.
So what's the difference? So I can write here as a component, I can write F is FU plus FV. correct?
Yeah, that adds up.
Here, if, so I will write it here. So the if u projection plus fv projection. Correct?
No.
So that's it. Big. No. So that's the difference between projection and the component. For the component, you can add them and you get the original one. For the projection, you cannot add them to get the original one. But the projection is what we get here. So the projection is when you go to the right angle. The component is, would be like that.
When do we use the projection?
Never.
Alright.
So here, just in case that we want to find them, if you have the angles, we have 15 and 45. So is 45. So projection at fu projection is f cosine 45, which is how much is the f? F is 100 Newton. Let's see what's the 100 Newton. So that's the 100 cosine 45. And FV projection, F again cosine 15. 100 cosine 15. So the value that we are using, so for both cases, it's going to be cosine. So it's going to be 70.7. And it's going to be 96.6. The only point is that if U and V are perpendicular, if U and V has a right angle to each other, then projection and component would be the same. Then projections and components are the same. So, in other words, if I have it like this, say U, it's a V, and it's a F. In that case, if U and if U projection would be the same, and if V would be the same as FV projection. So in this case, it's the only case that the projection and the component will be the same. Otherwise, the projection and the component will be different. So I'm going to write it on top. So this is the projection. This is the component. Because it always works with the Cartesian axis, and they're always as are perpendicular to each other. So always the projection and the components will be the same. So uh, sometimes we use this in place of that, or that in place of this without noticing. Any question? So we're going to do one more example on dot product, and then we'll move on to the next chapter. So we have our x, y, z, x, y, z there. And then we have this. And then I have the horizontal force. Okay. 300. Okay, so 6 meter here. Here. That's gonna be 3 meter high. 3 meter high. Point A, point B. So it says if you have, okay, so it's just like tripod, and then there's a force applying on that point P, pulling it to the right. Then want to see how much is the force along the AB and perpendicular to the AB. But most likely, what's the force along the AB? So look at it. If the force was already along the AB, the force was already along the AB, what would have done? If it was already along the AB, you would find the position vector along the AB, then the unit vector along the AB, and then the force along the AB, using the unit vector along the AB. We had it last time, using the position vector. So if it was along the AB, that was what we did. But it is not. So we have to find its projection along the AB. To find the projection along the AB, we have to use the dot product. First of all, you see the force is 300J. What does it mean?
Oh.
300J. What does it mean?
It's not in the wire. Yeah.
Means that it's parallel to the
Why?
Y. So it doesn't have an X or Z component. It's parallel to the Y axis.
Does that mean it has a magnitude of 300 along the y-axis?
So it's 300 along the Y axis, and 0 along the X, 0 along the Z. So if I want to find the component along that, so along that line, so if I draw that along that, and then find that component, so this is the FAB. So I know that if I want to find the FAB, the magnitude of the FAB, the magnitude of FAB is gonna be the vector FAB dot what? The unit vector along the AB. Right? So it says that if I have a vector and have a dot with a unit vector along the axis, it will be the projection on that axis. So if I want an FAB, I have to have the FAB and UAB. So the first thing I'm going to find the UAB. So to find the UAB, I have to find the RAB. So the position vector, what was the position vector? AB. So it's going to be the RAB, and this is going to be the UAB. So the RAB is going to be the second one minus the first one. Position of A. So what's the A coordinate? 0, 0, 0. What's the B coordinate? The coordinate for the point B.
Like 300.
The X is
It's the 2,
the X is
6,
2. The Y is 6. And the height is
3.
So the RAB that I want to calculate it is going to be XB minus, second one minus first one. XAI plus YB minus YA. J plus ZB minus ZA. K, so I can go ahead and say, hey, RAB is 0. The second component is all of them 0, but I'm just going to write it. So it's going to be 2 minus 0I plus 6 minus 0J plus 3 minus 0K. But in other words, the RAB is 2I plus 6J plus 3K. So that's the, and its magnitude is 2 squared plus 6 squared plus 3 squared. I don't know if I have it or not. I don't have it, can you give me yet? This is going to be its magnitude.
7.
How much? 7?
Yeah, 7.
Oh, sorry. So this is F, not FAB. So it's the F dot. It's the F because it's a force F, not FAB. We want to find the FAB, the magnitude of the FAB. So the unit vector, the UAB, is going to be RAB divided by RAB, which is going to be 2I plus 6J plus 3K and divided by 7. So if you do that, the UAB, if I've written it correct, it comes at 1286I plus 0.857 K plus 0.429K. So this is the UAB. So up to here, I find this. The F, I already have it, so I can just go ahead and find the magnitude of that. So if so the magnitude of that FAB is F dot UAB, which is F is 0I plus 300J plus 0K, and UAB is 0.286I plus 0.857J plus 0.429K. Which is going to be the X, Y, Y. So X component, Y component, Y component, C component, C component. FAB is going to be 0 times 0.286 plus 300 times 0.857 plus 0 times 0.429. So x, x, y, y, z, z. And she found that 257.1. So that's the magnitude of that FAB. So that's its magnitude. Now how can I get its vector? This is its magnitude, so the next part that it was about its vector. Remember that if you have said that it's the FAB was equal to magnitude times the unit vector. So it's going to be its magnitude times the unit vector on the AB, which is going to be its magnitude is 257.1 times 0.286I plus 0.857J plus 0.429K. So vector would be, if I write it correctly, so the 73.5I plus 220J plus 110K. And the last part, I'm not going to write it, it's just simple, that part. Because if this is 1 and if you want the perpendicular one, let's say this is the F. And the perpendicular one can simply say it's the F minus FA. I just simple subtracting. So in other words, if I want to write it, then 0I plus 300J plus 0K minus that 73.5I plus 220J plus 110K, and just I minus IJ minus JK minus K. But question? So let me go over that very quickly. What I did is that I want to find the magnitude of, I want to find the vector. So So if this is the f, I want to find the FAB. And here, quickly, what I did is that I have a f, I want to find the FAB. So to find the FAB, I need its magnitude and its direction. To find its magnitude, I use this equation, the dot product, which is f dot UAB. So I find the UAB here, use the dot product to find its magnitude, and then I use this equation to create it in the Cartesian for its direction. This part we had it before, the only part is that we just get the magnitude from the dot product. So that's the last time we use the dot product.
Next.
So this is chapter 2. Up to here, what we had is basically production.
Yeah.
None of them related to statics. Some of those materials you had it in physics before, and some of them you had it in maths before. So these basically the first 2 chapters mostly had.
Yeah.
So this is just a review of materials, so you can use them there. Chapter 3 is the first chapter that actually we are starting to look into. There's I can say, first chapter that's more directly related to the statics. So, chapter 3 is the equilibrium of the part. We're going to look at how the particle can be in equilibrium. And we'll get to that slowly. So, this is the equilibrium, this chapter. So, the equilibrium itself is that when I said there is an equilibrium, remember when we talked about equilibrium is that if I have that, whatever, is an object, whatever state it is, it's going to be a state at that state. In the statics, we are not dealing with the motion, so we're more dealing with the particle at rest. So we said if the particle is at rest, or if the object is at rest, it's going to stay at rest for gonna move. So if I have the object like this, and then assume there are some forces applied on that object. F1, F2, F3, F4. So I have an object, some forces applied on it. Or I have a particle. Remember what's the particle? The particle is that I can basically concentrate the mass in a single point. Particle is when I can concentrate the mass in a single point. So everything is going to be in the very single point. If I have particle like this, and then I have force applying that again. F1, F2, F3. What's the condition for either of these two to be in equilibrium states?
Zero net force.
Zero net force. So it should, no force, not that no force is applied on that, but if I add all the forces together, it should become zero. So for either of these two to be in the equilibrium, I have to have sigma F is 0. Same here, sigma F is 0. So if I have all the forces together, it should not move. So that's the basics of what we will do in this chapter. The entire chapter we are going to talk about it. Okay, is this object in equilibrium, or if it wants to be in equilibrium, what's the requirement, what's the condition, what should happen so that object stays in equilibrium. So one more time, look at here. This is an object in equilibrium, this is a particle in equilibrium. We are, in this chapter, we are dealing with the particle. Okay? So, and then later on we get to the object. Like a couple of things before we get to that. One of them is that I want to talk about the free body diagram, but before that I want to talk about the support. So what's the support? For this chair, for this table here, what's the support for this table? Why this table doesn't fall? Why this table doesn't move?
Legs.
What?
Legs hold it up.
What's going on?
The
The legs?
hold it.
But assume the legs is part of the table.
Normal force.
Where the normal force comes from?
Gravity.
Oh,
The Newton's third law.
well,
Newton's third law. The ground pushes back up.
good. But easier than that. It comes from the
Ground.
ground. So the support is what holds the object in place. Whenever we are talking about the support, is that what holds that object in its place? What doesn't let it move? So if I have a chair or a table, the support for that table or chair is going to be the floor or the ground. It's going to be here. That's the support for that. That's the one that holds it in place. It doesn't let it move. If I have, for example, a box hanging from the ceiling, so I have a box. Hanging from the ceiling. So that ceiling is going to be your support. That ceiling is actually holding it in place. So whatever hold the object in place, and later on we are going to talk about a couple of different, many different types of support. But here in this chapter, to start, we are going to talk about three simple supports. One of them is spring. So if I have a spring and something, so if it is like that, and then there's a force. That spring hold that force in its place. Eventually that spring stretch, but then hold it. After it becomes in the equilibrium, when you apply the force, the spring stretch, and then it gets to the state of equilibrium. It doesn't move. So that spring is support there, holding it wherever it is. So assume you have a spring and you hang a box of that. So the spring is stretched and then hold that box in place. So that the spring is going to be the support. You have this in physics that the F is K delta L. K was the spring constant or the stiffness of the spring that you are going to work with that, and delta L is the deformation in the spring. So the K basically is the spring constant, or it's going to be the stiffness. And delta is just deformation. How much it deformed, how much. So delta L would be initial is the final length minus initial length. How much it changed. The second one is cable and pulleys, but mostly the cables. So I think this slide quite hard. That, and then there's a pulley, and then so there's a cable going on like that, and then there's a force. There. Poly T. For the cables, there are 4 conditions that you have to consider. The first condition is that the cable has no weight. cable does not have any weight. So in analysis, we are not consider that. The cable cannot stretch, so it's not flexible. It doesn't. Its length doesn't change. The next one, only support tension. So remember, the cable only support tension. If I have a cable, I can pull it. If I push it, it doesn't do anything. So you cannot use the cable as a support for anything else unless it's in tension. Okay? And the force, and it's also important that for the cable, the force always acts in the direction of the cable. So, force always only act in direction of cable. So for example, here, if this is the cable, if I put a force like this, horizontal force there, what would happen? It will move. Correct?
Yeah.
So it doesn't do any support. If I want to make sure that the cable does support, the force should be along the cable. So that's why I drive along the cable. The tension or the force would be always along the cable. So wherever we have the cable, the force is along that cable. And the last one, the last support that we're working here is the smooth contact. So for the smooth contact is that we have, for example, if it's on the ground, something like that, and in that case, so I have the weight and then the reaction of the support. In the smooth contact, the reaction of the support is always perpendicular to the support. So here I have the reaction of the support. It's going to be like that. And it's going to be perpendicular to that point that you're talking about. If I, for example, assume I have something like this. Okay, and then I have a ball sitting here, connected with the rope, that wall. So what do I have there? The forces that I have. So one of them is going to be the weight, the one that wants to move it. So the weight is going to be there. So the weight would be there. What else is there?
Is it on like a random tension?
The tension of the rope. So there's a a rope, so it's gonna be the tension of the rope. The tension of the rope is gonna be along the rope, and we are gonna pulling it, so it's gonna be that way. Because it wants to hold it here, so it's the tension of the rope, like this. And then normal for the support, which would be at the smooth contact here, normal to the surface. Right?
Yeah.
Okay. So these are the three basics supports that we are gonna work with. So I'm going to stop here. So next time we'll start from the free body diagram. I'll show you how